So it's the right one. So it's going to be page 39. All right, let's go. Class?
Yes.
All right, so I'm glad all you people have decided to make it here, even though some people did not make it on time. Okay, they did not beat the buzzer. So we are on page 39. Oh, come on, work. No. There we go, 39. So Hamilton paths and circuits. So this has to do with the stuff that we talked about last time. Eulers from yesterday. Eulers had to do with the edges. I had to cover every single edge. But a Hamilton is I cover every single vertices. So now we think about that because on yesterday we were talking about going trick-or-treating, right? Yes? Okay, we're going trick-or-treating, and was it someone in this class that said they made like $70?
How did they do that?
Went to the rich neighborhood? No, they give out cash.
Well,
Like straight up, yeah. Okay, you know, like you go to the rich neighborhood anyway because they got the full-size candy bars, right? But they also, the guy was telling me, he's like, yeah, I made like $70. They give out cash too. Sometimes 5s, 10s, yeah. So, you go through the neighborhood and whatnot, so you do a Euler circuit, but you want to let your homies know, you're like, yo, hey, you guys got to hit up these houses. And so you're going to mark each one of those houses. So are they going to cover every single street? No. They're only going to go directly to those houses that are handing out cash. Right? Because that's what a good homie does. So you're going to mark that, and so what you're going to do is you're going to create a Hamilton path or circuit. What's the difference between a path or a circuit? Circuit goes around, right? And comes back to beginning, and path doesn't. They end at different places. Does that make sense? Okay, so same rules apply that when we were going through and actually doing all the edges and all that stuff, same rules going to apply about the odds and evens and all that. So right here, Hamilton path, Hamilton circuits. So we're going to go through and map those here in a moment. Blah, 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 blah. Okay, here it is. A path that passes through each vertex this time. Hamilton has to do with vertex, where Euler is the edges of a graph exactly once is called a Hamilton path. Because if you try to go to those rich people's houses that are handing out cash on Halloween, yeah, you know they're going to like kick you out or something. They're like, yo, weren't you just here? Give me more money. No. Anyway, if a Hamilton path begins at the same vertex and passes through all other vertices exactly once, it's called the Hamilton circuit. Make sense? Yes? Hopefully? Okay, you guys are like super excited right now. You guys got excited because, you know, hearing about some rich places giving out cash for Halloween. You guys made it this many years and never even knew that? That's why I always go to the rich neighborhood.
I mean, you live in a rich neighborhood.
I wish. I live where the hills have eyes. I'm telling you, you don't. Yeah, they come out and tell me we don't take kind of your kind in these parks. Yeah, I gotta worry about that more than anything else. No, seriously, no trick or treaters. I see more bobcats than I do trick or treaters.
They live in the hills.
Yes.
Oh damn.
So yeah, I didn't realize how beefy the bobcats are here until there was one in my yard. Yeah, an actual like. We're talking like a mid-size. I'd say like a pit bull, but he was like a beefy pit bull. Not like those little weenie ones that don't ever do anything and just sit on the couch all day, but the ones that actually go and like work out all that. Yeah. Anyway, but still, yeah, this guy got some beef on it. I don't know. Can you say it had beef? It's a cat.
Yeah.
So it's a beefy cat. Okay, good. All right. So Hamilton circuit starts at one place and goes all the way back to that same place. And I know no one else is playing with their phone right now because. Find a Hamilton path for the graph. Hamilton path goes through every place how many times? Once. Goes through every single time once. Okay. So let's see. Watch this, watch. Path is easy, because all I have to do is connect the dots. Bam, bam, bam.
Oh, you don't have to hit every single edge.
I don't have to do the edges, I only have to do the vertices. So that's why I said this one's easy. Connect the dots, yes you may. No you may not, because you had your phone out. I don't care. That's what you're supposed to do anyway. All right, so my solution for A, problem A, is going to be A, B, E, D, C. So, I hit every single one once. Now, I'm going to erase this one, and I'm going to do another one. Actually, do you know what? I don't think I have to erase it. Let me pick a horrible color. This one right here is a horrible color. So now, let's do a, wow, that one is pretty bad. Okay, there we go. So we're going to start here, and we're going to do a Hamilton circuit. So the circuit's got to be different, because the circuit has to end where? At A. For this case, it's going to end at A.
Where it started.
So I'm starting at A, I'm going to have to end it at A. So I can't use the same pathway that I did. So I'm going to have to take a different route. So I'm going to go, near, and there we go.
You can do that.
Yes. Did I go through every single one once?
Oh wait, so the Hamilton circuit just doesn't touch every edge also.
It doesn't need all the edges.
Just the
It
vertices.
just needs
So
to
Hamilton never needs ever needs to hit every edge.
Not the edges, it needs to hit every
Vertices.
vertices. There we go, perfect.
Yeah, the
That's
Hamilton
that.
does
Yes.
not need to hit every edge though. No matter circuit or graph. I mean circuit or path.
Fire.
Yep. Same thing? Yeah. Really? Really?
This finger,
Uh-huh.
this finger, this
Uh-huh.
finger, this finger.
Yeah, you better put your earbuds away too while you're at it.
Well, you can see that?
Uh-huh. Yes, I can. Your ears are kind of out there. Anyway. So, I'm going to write down my answer now. There we go. Okay, so for part B, I went A, B, E, C, and D, and then back to A. So that's how you write your answer, describing your path, because you're giving it point for point. It's like you're like hiding something over here. Oh, it is. Put this right here. Are you writing stuff down? No, exactly. You just asked the same question about like, oh, that's how we write this stuff? Yeah, maybe a little bit less phone, a little bit more notes. How dare you? You know what? That's it. I'm gonna go put this on the charger for you. See? That's how mean I am. I'm gonna go put your damn phone on the charger. All right. Make sense now? Alrighty, so let's take a look at this. A complete graph is a graph that has an edge between each pair of its vertices. Okay? Each pair of its vertices. So is there over here in between each vertice? So let's see. It says not a complete graph because there are no edges for connecting the vertices A, D, B, and C. It says right here that this is a complete graph because there are edges connecting the vertices A, D, B, and C. A, D, B. But the problem is, I don't like this answer because this one actually is still not. Is that connecting A and C? Because is it connecting A and C? No. Am I going directly from A to C?
No.
No, they're not. It's going through E. So wouldn't that be the same reasoning that this one is not, because it has to go from A to E to D, to make this one not, right? This one doesn't have a line connecting A to C. That's what's missing there, because there is a stop right there. So there's an edge for AE, and there's an edge for EC, but there is not an edge for AC. What you missing? Huh?
The homework?
Oh, it's right here. And the same thing goes for over here for BD. There's also that one that's missing. So this one is not because of that. Now, the number of Hamilton circuits in a complete graph with n vertices is n minus 1 factorial. All right, let's look at this last one. 1, 2, 3, 4, 5. How many vertices were on that last one?
5.
5, very good. So n, which stands for the number, right? Because we had that last chapter also. N stands for the number. The number is what? 5. Number is 5. Are you writing that down?
Yes.
Are you on the right page too?
Yes, what? You're doing good.
You know we're down here, right?
Yes.
What's the number?
5.
Okay, what should you write down? See, that's what I was worried. You didn't have it. And you're like waving the paper at me for some reason. Trying to check on you, make sure you're all right, but no. All right. So, n minus 1 factorial means it's going to be 5 minus 1 close factorial. What's 5 minus 1?
4.
So, 4 factorial is going to be 4 times 3 times 2 times 1. That's what factorial means. It's a mathematical term, factorial. Don't look at me in that tone. So, factorial, whenever you see the exclamation point, it means it's going to be 4 times 3 times 2 times 1.
If it's 5 factorial, would be like 5 times 4 times 2.
Yes, it would.
Okay.
So if it was 5, and it's always just going to be all the numbers from that number down. Yep.
That's the answer?
So let me see. What's 4 times 3?
12.
Times 2?
24.
Times 1?
24.
So how many possible, the number of circuits that we could have? Yeah, there's going to be 24. That's why. There's going to be 24 different possibilities. Yes, does that make sense or no?
Yeah.
Now,
Go.
so here's the math for this one right here. For the one that we just did. So, they gave you another one that actually had 4 of them. So, Hamilton, okay, 6 different unique Hamiltons. So it would be 4 minus 1, which they're using the formula here. 4 minus 1 gives us 3, and 3 factorial is just 3 times 2. And listing all the possibilities, when you're doing this, please pay attention. When you're doing this, okay, if it's a circuit, don't they always have to start and end at the same place?
Yes. Correct.
Very good. So, we're starting with A here. And what they did is went A, B, C, D, and then ended with A, because it came back down to A. The next one is A, B, but then just switched C and D. And the last one has to end with
A.
there we go. And so that's what's happening there. So now we got both possibilities with the B in the second place there. Now, we put C in the second place. We put C in the second place. A, C, B, D, and it ends with A, right?
Yeah.
And so with C in the second place also, I'm going to have A, C, D, B. You know, I'm just switching the ones that were right in front of it, and the last one ends with A, right? So that's the way to actually go through and list all the combinations. And once you get those two there, then you get down to having D in the second place. So we go with D in the second place, and then it goes BC, ends with A, and then change it to CB, and then ends with A. So those are all the different unique possibilities for this. Does that make sense, or is that nonsense? Kinda? Okay, good. So it will make more sense here in a moment when you're actually trying to do this for like a reason.
Yeah.
Right now, this is just formula. I'm telling you what to add and multiply. Do we do this one? Yeah, we're going to do the weighted graph. A complete graph whose edges have numbers attached to them is called a weighted graph. So a weighted graph is numbers shown along the edges if a weighted graph is called the weights of the edges. So now think of it like this. You're looking at a road map. You're going in between two different places. So if you take this one pathway, that one's going to be 5 miles. But if you take the left turn instead, that one's 7 miles. But they'll both take you to the same place. You're like going to, taking a shortcut. Leaving your house, heading down to Circle K. You can go more than one way to actually get there. One way might be longer than the other. Those are the different weights on this. And it's used a lot with maps. And it's used a lot with travel. And we're going to do a travel one here in a moment. So I know you guys are trying not to fall asleep. I appreciate it. But let's just do this, and then we can figure it out. Because to be able to do the homework problems that we're going to start on, you need to know this one. All right, the graph below is a model graph for one-way airfares for cities A, B, C, D. Use a weighted graph to find the cost of the trip for the Hamiltonian circuit. So we're starting where? We start at A. So I'm going to go there. From A, where do I go?
B.
I go to B. Okay, so I know my value is 190. So it's going to cost me 190 to go from A to B. And from B, where do I go? I take D, right? Are you guys not paying attention? I am following that right there. And so that next pathway was 155. And then from D, I go to C. That's 179. And from C, I go back to A because this is a circuit. I have to end at the beginning, which that one was 124. So add those up for me, please. Six what?
648.
648. So that is the cost for the airfare of traveling through those cities. Right? Some of you guys are going to be like pro ballers, right? So you're going to go on like a, I don't know, like away games. They have a bunch of away games at once, right? Basketball players, right? Yeah. That's what pro ballers do?
Yeah.
Okay, so they go and there's, referred to as like a road trip. So what they're going to do is they're going to go from here to here, right? And then they're trying to actually get this in order. So here, 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 and here. What the hell's that?
No clue.
Make sure you keep the door closed. Bunch of weirdos out there. Anyway, so those pro ballers are going to go through, and this is going to be the cost for them to go to those other cities, play the basketball games, and come back, right? Say yes. Okay. Now, we're going to do something else to come along with this after on the next example. So, I'm going to pause right here. This is where you guys are going to start working on the assignment. All right. One more time, class.
Yes.
All right, so we're going to finish up our notes here. I'm going to do a last little bit because no one's playing with their phone right now because we're finishing our notes like good students. And it says traveling salesperson. This is where a lot of this comes into play. So traveling salesperson problem is a problem of finding a Hamilton circuit in a complete weighted graph which the sum of the weights of the edges is a minimum. Minimum. What do you think minimum means? Smallest number. So I need to go through all this, all my vertices, and have the smallest number possible. There we go. All right, so such a Hamilton circuit is called the optimal Hamilton circuit or the optimal solution, or just optimizing it. One method for finding an optimal Hamilton circuit is called the brute force method. Brute force is going through and trying everything. But it's really not that complicated if you follow the steps. So I'll show you kind of brute force, and then I'll help you to make it easier. So, right here, model the problem, complete with weights, determine the sum of the weights, edges, and calculate. How many vertices are here? There's 4 vertices. So my n value is equal to 4. Or say n equals 4. So that means to figure out how many I would have, I would go 4 minus 1 close factorial. That's going to be 4 minus 1 is 3, right? So that's 3 factorial, which turns into 3 times 2 times 1, which gives me 6. There's 6 different possibilities.
I don't get it. Why is it 4? Why do you have to make it factorial?
From the formula. I think that was before I put your phone on the charger.
That was the brute force. No, I remember the formula. That was the n minus 1.
Yeah.
But so the solution is that's how many like.
No. We haven't got all this yet.
Oh, okay.
We haven't. I just need to brute force. How many different pathways am I going to have? I'm going to have 6. So brute force means I'm going to list every pathway and then calculate the weight.
Okay.
Does that make sense now?
Yeah.
So this tells me that I'm going to have different combinations. And so if I'm going to start at A, like we did on the last one, right? So I went A, what was it? It was like because A, B, C, D, A, right? And listing all the possibility, my next one would be
A C.
A, say it again, A what?
A C.
B, one more time,
A B C. A B D C.
D, C, and then,
A.
very good. So now we got those switched right there, right? So the next one would be
A C.
A, C,
B.
B,
D.
D, oh that's a B, I'm sorry, D, A. You guys seeing the pattern here, hopefully?
Yes.
C.
The next one is going to be A, C,
D.
D, B, A. My last two is going to be A what?
A B.
D,
C.
A, D, just to show this. This is going to be
C.
C,
D.
B, A, and then it's going to be, so it's going to be B, C, A. So there is a pattern to list all your possible choices there. Now using brute force is you're going to go through and find every single value. So to calculate this one, I'm showing you all the steps, but I'm not going to expect all the steps here later on, here in a moment, okay? So, right here we have A, B, C, D, A. So it's A, B, C, D, A, which came out to be, what was it? What was the number? 6 something? 648. Because this is the one that we did earlier. So the first one is what we did earlier. 648. And now, I want you people doing the same thing, but I want you calculating it, going through and calculating your values. So, are you worried about passing the math class or, your Chewy bars?
So are those all possible like answers? Are all correct answers?
Yes.
So you have to-
All the possible different routes you could take. So if we do this, because remember, it's not going to be every single edge. If it was every edge, that means every single time there would be the same value, right? But if you look at this from what I did before,
It's different, right? Yeah.
I skipped this side and this side right here, right? So I'm going to skip at least 2 of them every time. I just want to try and get the smallest number out of it. There we go. So you guys are calculating this, right?
So you just want to get a smaller number.
Calculate each one. That's what brute force is.
Yeah, this one.
Okay. Tell you what the brightness of over here.
Oh, we're on this one.
Yeah, we're doing this right now. So we listed all the possibles, and then now we're calculating.
Well, when did you get 648? How'd you get
That was from the previous problem. That was before we took a break.
I used to hide some of this.
It was over
I
here.
didn't know.
You write it down. So just add together the pathways that we took.
If you're adding,
So,
no matter which way you flip it, it's gonna always.
no, it's not, because we're skipping some edges.
Oh, it's just A to B.
A to B, yeah, so that A to B is 190.
190, B to C is 126.
Yes.
B to D is,
Does that make sense now? Okay, good. Anyone else need help? Yeah, that's what we're doing right now. So you're doing, in the second one, A to B was 190, right? Plus B to D, so B to D is 155. Right, so you have to put that. Plus, and after that is D to C. D to C is, did you already know? Yeah, there's a lot of water. I wanted you to actually do the math. Do the math, and I'll let you go.
Okay, cool. Problem?
Yes. Mm-hmm. Yeah. Just copy it. So much. What above? Enter, and then you could change it. So, was it 153 or 155? Uh-oh. Right. Yes, that guy.
B to D is what? Is it 179, 124, 55?
B to D,
is,
it's right here, 155.
oh,
So if you guys want to flip back a couple slides, it is bigger a couple slides earlier, so you guys can see it. Right in the middle of the page.
so C to A would be 124?
C to A? Yes.
A to B is
So, here, right? So AB is 190, and then B to C, B to C is 126, and then C to D, 179, and then D to A is 157. So we add all those together, and then we get the number. No, you go this order.
So order that from then?
Yeah, that this is it.
Finish it, Spacho.
Okay, so yeah, there, you should skip 2 every time.
Didn't we already do it? Wasn't it like nine?
Must have been second.
All right, what's the optimal?
No, because we
C to D.
Oops. This one looks like it's a lot less. So which one is the optimal? What's up? 5 what? Say that one more time. 529? She's got something else.
You make it. Ain't that enough.
I want speed.
That's the lowest number I got.
I know. Did you come up with it? No, yet.
No.
He doesn't have 529 either. Check your numbers on that one. So. I don't know if you can see it.
I don't even use that one.
All right, let's see what we got. So after we go through and fill this out, let's see, BD. Where's it? Here it is. AB. AB, DCA. That one was it 648?
Yeah.
Next one was 562. Next one is,
648.
next one is,
652.
last one is 652.
Oh, that's big. Right.
All right, so we're looking for an optimal solution now, right? Optimal. So minimize. So what's going to be my smallest number here?
562.
562. So I can take this route or that route to actually pay the smallest amount to actually go to in between every single one of these places. So that's the key. Okay, and if you're having trouble with adding them up, it's also right here on the next slide. Well,
You know,
Wow.
that's evil.
Wow.
We did all that.
Pasha.
We did all that.
no, what do you mean for nothing? This is actually good practice. If you're looking at it right now, you're like, oh crap, how do I find that? Or, actually putting it in yourself is important. And if you're struggling with it, here's where they come out to be.
Is there gonna be like a thing on our calculator where
No.
it does it for us?
No. All right, so go ahead, get out. So here's the two optimal solutions. Okay. Now, this next one is called the nearest neighbor. So instead of doing brute force, that's brute force, listing them all, putting all the combinations there, and picking the one that's the cheapest. Okay? That's what brute force is. This nearest neighbor method. It's not always 100% correct, but there is a chance that it is. So it's a good chance that it is. So right here it says, model the problem with a complete weighted graph, identify vertex as starting point. From the starting point, choose the edge with the smallest weight. Move along this edge to second vertex. Second vertex, choose the edge with the smallest weight. And that does not lead to a vertex already visited. Move along this edge to a third vertex. Continuing, building the circuit one vertex at a time by moving along edges. Smallest wait until all vertex is visited. From the last vertex, return to the starting point. Now, there's one problem with this. Sometimes it's not going to give you the optimal, because you're going to end up having to take, if you go the shortest route, you might have to take the longest one in there. So what you really want to avoid is the longest one. So let's take a look here. Which one right here is the most costly if I'm just looking at the diagram? I heard it? A to what?
E to D, A to B.
E to B, right? That's 195 here.
Oh.
Yeah, 195 is there. E to D is 194, right? So there is a difference. But you want to try and make sure you're avoiding the most, if at all possible. So this one right here, sales director who lives in city A. So that means they live there. They need to go to all these other places. Required to fly to the regional offices in the different cities, B, C, D, and E. The weighted graph shows one-way airfares. Use the nearest neighbor method to find the approximate solution. What is the total cost? So, if I'm starting at A, which way should I go first? Should I go to B? Should I go to C? Or should I go to E?
D.
Or D? Which one?
C.
Why C?
Because it's the lowest cost.
It's the lowest. Here's 180, 114, 147, 128. You want to take the smallest value all the time.
Yeah.
Now from C, am I going to take the 169,
To E.
the 115,
B.
or 116?
116.
I want to go the 115, right?
So E.
So if I take the 115, I'm over here at E now.
Okay.
And then go back to B.
And so from there, but there's a problem. Did I visit everywhere?
No.
No.
I have not visited everywhere yet.
So
Where do I still have to go?
B and E.
Okay, so which one am I going to go to first? Am I going to go to D or B?
D.
Okay, so let's go here. Then B, and then finally up to, there we go. So that one right there is the nearest neighbor. Every time you go to the nearest neighbor. Is that one always going to be optimal? No. I bet you could probably find a cheaper one on there. If I was going to do this again, which routes do I need to try and avoid?
195.
I want to avoid the 195 and the 194.
Yeah.
Wouldn't I want to avoid those? So let's see what this cost is going to be. So for my solution, we said was A, C, E,
D, B. D, B.
D,
B.
B, A.
and what was the cost?
114, 115, then 194.
Yeah, start adding them. So it's 114 plus 115 plus 194 plus 145 plus 180. What is it? 748? Okay. There we go. 748. Now, do you think we could get a cheaper one there?
Yes.
This is the nearest neighbor method. So it's a method, and you always should get the same value when you do nearest neighbor. But let's see if I can actually do this by avoiding. I'm going to do this by avoiding now. So I don't want to take 195, 194. So I could do 114. So instead of taking the 115, could I do 116?
Yeah.
Okay. 145. Where else? I could go 194. And then, so I'm avoiding a couple different ones there. What did I get by doing that?
6.
Let's add them. So A
697.
697. I heard it. So
14.
so is the nearest neighbor method always the cheapest? No. But it's going to give you one that shouldn't be the most expensive. That's one way of trying to minimize the values. You guys agree with the number 697? Everyone? Yes? You agree?
There's one more cheaper.
Huh?
There's one more cheaper.
Is there a cheaper one? You got, oh, what'd you get?
I got
Do
100.
you want me to erase it? Here. Let me do this. All right, so where'd you start?
128.
You did
128.
128.
Then
Hold on. So 128,
then 150.
115,
160.
116,
Then the 145.
145,
Then the 147.
147.
And I
And
got 651.
651?
Mm-hmm.
Oh, good job. So, how'd you do it? You just tried to avoid the highest ones, right?
Yeah.
There you go. Not bad. All right. So, other than that, that's what I have for you. And the next one right here is them, like, I made it bigger so we could see what we did earlier.
So for that one, you can cross over the line, right?
Yeah, you can cross, but you can't, if you notice there, where they cross, that's not a new point.
Right. So you just can't cross vertices?
Yeah, you can't go with the vertices more than once.
Oh, okay.
All right, other than that, that was the approximate using nearest neighbor, but we still came up with the better. So make sure you guys like, share, and subscribe, hit that notification button, and support my channel. Use promo code
Early bird.
EARLYBIRD, get 10% off the merch store.